So we discussed the three different definitions of acids and base, but from here on out, our discussion would mainly focus on aqueous solutions and using the Bronsted-Lowry definition. Sometimes we would use the Arrhenius definition to simplify some of the writing, but generally speaking, what you should imagine about acid-base reaction is based on the Bronsted-Lowry definition. Another important thing in the Bronsted-Lowry definition that we need to highlight is something called the conjugate acid-base relationship. And this is the idea that with the Bronsted-Lowry definition, whenever there's an acid, there's always a base. And it turns out that on the product side, you also have acid and a base present. And let's take a look at an example reaction, which is shown right here. So on the left side, you have acid represented as HA, and then you have the base represented as B minus. And of course, the Bronsted-Lowry reaction tells you that the acid is going to donate its proton and the base is going to accept it, which means on the product side, you will have HB as a product and then A minus as the other product. Now, if you're looking at HB and A minus and going the opposite way, so in other words, this is a reversible reaction, you can see it going to the left. HB and A actually acts as acids and base, right? So it's pretty clear that HB is an acid and then A minus, it's a base because it goes to form HA and B minus. So what this is saying is that the acid on the left, HA, becomes a base, A minus, on the right after it loses the proton. And so that base is what we refer to as the conjugate base of the acid. And then HB is the conjugate acid of B minus. So the relationship is between these two, the base conjugate acid relationship, and then these two, the HA and A minus. So HA and A minus, and then B minus and HB. So we would say A minus is the conjugate base of HA, or HB is the conjugate acid of B minus. One of the interesting things about some chemical species is they can act as both acid and base. So this is what we refer to as amphiprotic, or more generally amphoteric species. Water is an example of this. Here's a reaction where water acts as an acid on the top. So you can see your ammonia and your water forming ammonium and then OH minus. So the water has lost the proton here, right? So water is your acid, and then OH minus is the conjugate base of water. I'll use the same color for the conjugate acid-base pair. And then NH3 is the base. And then ammonium is the conjugate acid, because compared to NH3, NH4 plus has one more proton. So again, the way you tell the conjugate acid-base relationship is just by checking if the relationship is different by one proton. If it is, then that's a conjugate acid-base relationship. Now, here's the interesting thing. Water, as I said, could also act as a base. So if you look at the second reaction, here we have HF and water producing H3O plus and F minus. So HF is your acid in this case. How do I know that? Because it becomes F minus, so it loses a proton. So F minus must be the conjugate base. So again, I'll change the color, make sure I denote the conjugate acid-base pair. Water in this reaction acts as a base, so H3O plus is its conjugate acid. And how do I know? Because they differ by a proton. That's what we said earlier. And then this one also differs by a proton. So you just see water in these two reactions, one time acting as an acid, another time act as a base. So that's what we refer to as amphiprotic or amphoteric species. You can do this with all kinds of reactions. So here's an example. You have to write the reaction of the bisulfite ion as an acid and as a base. So bisulfite is also an amphoteric species. So as an acid, it's reacting with OH minus. That means that it has to donate proton. So therefore, the product is that once it donates proton. And so, of course, the OH minus adding that proton to it becomes water. So this is our acid. This is our conjugate base of the acid. This is our base. This is our conjugate acid of that base. You can write bisulfite, HSO3 minus, as a base. Now it's reacting with HI. Make sure this is written as equilibrium. So if it's a base, it accepts proton, so it becomes that. And then the HI just forms I minus because it gives away the proton. So now HSO3 minus is a base, and this is its conjugate acid. And then HI is the acid, and I minus its conjugate base. So you want to be able to write both forms of the reaction. You want to know how to write a reaction when you have an acid and a base given to you, how to write the product as a conjugate. Now, Once we know how to write these reactions, the next thing we want to think about is the strength of acids. The reason why HSO3 behaves differently when it's paired up with OH minus versus HI is because there is differences in terms of the strength of the acid and the base of HSO3. So the acid and the base role could be changed depending on who the substance is reacting with. So in order for us to know who's going to behave as an acid or a base, we're going to need to rank them based on their strength. So this is why we get into this topic of acid strength. So there are two ways we can calculate or quantify the strength of an acid. The first is something called percent dissociation or percent ionization. And the way this is calculated is just by first starting with the reactions, the acid dissociation reaction. So just HA goes to H plus and A minus. You can see here I'm simplifying my writing using H plus instead of hydronium. But since it's an equilibrium, I have some starting HA concentration, and at the beginning I don't have any product. Some of this acid will dissociate, so minus X plus X plus X, and so I have some quantity of product that's generated at the end. And so the percent ionization is simply just how much product I have, in this case using H plus as the measure of the product, since that's the species that matters in an acid-base reaction. So H plus at equilibrium divided by the starting material, which is HA initial, multiplied by 100%. So if this number is large, that means that most of the acid you start with becomes H plus. In fact, if the percent ionization is 100%, these are what we call strong acid. And then if it's less than 100%, we would refer to them as weak acid. Now, of course, there's a large group of things that are strong and a large group of things that are weak. You can be weak if your percent ionization is 90%. You can be weak when your percent ionization is 9%. So there's a large continuum as far as how weak the acid is. So we're going to need another number to better measure the strength of an acid, and the second number is the acid dissociation constant, which is an equilibrium constant, and it's given the symbol Ka. So Ka, just like any equilibrium constant, is just the ratio of the products over reactant at equilibrium, as shown here. So that refers to that acid dissociation reaction on the top right, so you get the products over the reactant. Both of these quantities should be related to each other. So for example, you can calculate the Ka if you know the percent dissociation, or if you know the Ka, you should be able to calculate the percent dissociation. Here's an example. Okay, so it's asking us to calculate Ka of nitrous acid that is 6.5% dissociated. We know the formula of nitrous acid is that, so we can write its dissociation equation. So the Ka, if you want to calculate, should then be the concentration of H plus times NO2 over HNO2, all at equilibrium. The question is getting that equilibrium number. Well, we started with some quantity. We were told it's 0.125, and then we lose some, make some product, and then at the end we have X of these guys and 0.125 minus X. Well, we were told that the acid is 6.5% dissociated. Remember that the definition of percent dissociation is concentration of H plus, which is X at equilibrium, divided by the beginning concentration of the acid, which is 0.125, times 100%, and that's equal to 6.5%. Now, when you have that set up, you can solve for X, which is also the H plus concentration. So the X value here would just be 0.008125 molar. Again, that represents H plus concentration. Now, once you know H plus concentration, since that's the same as NO2 concentration, you can then plug that into your Ka expression. So if you take this number and then you plug it back into the Ka expression, along with the HNO2 concentration at equilibrium, you should be able to calculate your Ka. So I'm going to just do it real quickly here on the top. Ka is going to be 0.008125 multiplied by itself, right? Since NO2 is the same, so it's just squaring that, divided by 0.125 minus 0.008125. That's the equilibrium concentration of the reactant, and you should get 5.65 times 10 to the minus 4. So we just discussed these two measures of acid strength, which is the percent ionization as well as the equilibrium constant. Now, the equilibrium constant for acids have been measured for many acids. So this table here is in your lecture notes, just an example of what we call a Ka table, which is just a table of acid equilibrium constant, or Ka, ranked from the strongest acid on the top to the weakest acid at the bottom. Now, specifically, when you're looking at the definition of strong versus weak, so there's stronger and weaker, and that's relative strength. And then there's also something we refer to as strong and weak. So strong here specifically refers to these acids that are above the hydronium ions. So 6 acids here are what we refer to as the strong acid. Highlight them as yellow, okay? And then everything else that's not highlighted will be considered weak acids. Again, stronger acids are higher, weaker acids are below. Strong acids are top 6, and all the other ones are weak acids. So I can say, reading this table, that H3PO4 is a stronger acid than HF. However, they're both weak acids. Okay, so keep in mind that's the terminology. On the right side of the table are the conjugate base of the acids that's shown on the left. So, for example, perchlorate ion, which is ClO4 minus, is the conjugate base of HClO4. Okay, you can actually know the formula of it because the conjugate base always has one fewer proton compared to the acid. Now, it becomes important to talk about some of these acids that we call polyprotic acids. Basically, that acids that can lose more than one proton. If you look at some of the acids we talk about, these are what we call monoprotic acids, and that just means that they can only have one dissociable proton. So HCl, nitric acid, cyanic acid are examples of these, and the reaction looks simply just like this: HA plus H2O, where A is, any of those anions, and then you produce one hydronium ion or one proton, and then the conjugate base. A diprotic acid would be something that can dissociate into 2 hydrogens, 2 protons, so it has 2 dissociable or 2 ionizable hydrogen atoms per molecule. So for example, H2SO4, sulfuric acid, has 2 ionization steps. First step is just losing that first proton and forming this as the conjugate base, which is the bisulfate ion. Okay, now it turns out that Ka, that first Ka, is really large. It's actually greater than 100, so we assume that the reaction goes to completion. All the acid that we start with becomes proton. So 100% dissociation, right? Remember that percent dissociation is a measure of strength. The second ionization, which is the bisulfate ion, reacting with water, forming proton and sulfate, has a lower Ka value. It's actually about 0.01. That second dissociation then doesn't produce as much product as the first one. So the first one goes to completion. The second one actually only goes much smaller. You can calculate the percent ionization of that step, but it's probably less than 10%. Now, a triprotic acid would be an acid that has 3 ionizable proton, and so phosphoric acid is an example of that. Here's the first ionization forming that product as the conjugate base, and then that ion, which is the dihydrogen phosphate ion, can itself react with water and produce second proton, and then forming that monohydrogen phosphate ion, and then that monohydrogen phosphate ion can then do another dissociation. You see here the Ka values are progressively getting smaller and smaller, which again means that there's fewer and fewer protons being produced as you go to the later dissociation step. In fact, it's not uncommon that successive ionization Ka values differ by a factor of 100,000 to a million. That's kind of what you see there, right? So the first one is 10 to the minus 3, the second one is 10 to the minus 8, so that's about 100,000. This actually is really helpful when some calculations later on because we can simplify our calculation. In the Ka table, the polyprotic acids are shown here as well, but they're just shown as its own acid. So for example, here's the H3PO4, and then here's the dihydrogen phosphate, which is the product of that first dissociation. You can see it here on the conjugate base side of things. That's the product, right? And then it becomes an acid again with its own Ka, and then producing this product. And then you see that the third one down here, that's the third dissociation, and then it has its own product as well. So what you want to keep in mind is that each of those has its own Ka value. So this is the Ka for the third step, this is the Ka for the second step, and right at the top there's the Ka of the first step.